Okay, let's keep learning about ionic bonding. The first thing I want to talk about is why electrons move from sodium to chlorine.
So, we already know that electrons move, Boba, from sodium to chlorine because sodium wants to get rid of one and chlorine wants to take one. But there is a little more to the story than that, and Tyler is going to tell us about that today.
And not from chlorine to sodium. Okay, so in the first step of ionic bonding, this one electron from sodium moves over here to chlorine to fill this one space. But people often ask, why couldn't these 7 electrons from chlorine move over and fill these 7 empty spots in sodium? Well, that's a great question. The answer has to do with a topic called electronegativity. Okay? Electronegativity is a measure of how badly an atom wants electrons.
Okay, so what is electronegativity? A measure of how badly an atom wants electrons. How good is it at pulling on electrons? And I need a copy of this book so I can know what blanks are there.
The higher an atom's electronegativity, the more greedy it is for electrons, the more it wants to try to steal them from other atoms. So in ionic bonding, there are electron givers and there are electron takers.
Who are the electron givers in ionic bonding?
Metals.
Metals, yes. Who are the electron takers? Non-metals. So who do you think has a higher electronegativity? Who wants electrons the most? Non-metals. Yeah.
This has to do with whether an atom is a metal or a nonmetal. Okay, so nonmetals, like chlorine, all have a very high electronegativity. Okay, they are very greedy. They want other electrons very, very badly. On the other hand,
okay, so you can fill that in where we have our nonmetals. You can fill in the word electronegativity. They have high electronegativity. Part of this is just getting you to write the word a few times so you can remember what it is.
And metals, like sodium, have a low electronegativity. Okay?
So you can fill that in. Metals have low electronegativity. They don't really want electrons that badly. They're kind of happy enough to give them away.
They're not so greedy for electrons, and they're willing to give them up. So that's why electrons move from sodium to chlorine and not the other way around. They move from the atom with low electronegativity, low greediness, to the atom with high electronegativity. And this is the way it always works in ionic bonding. The metals, like sodium, are the electron givers, and the nonmetals, like chlorine, are the electron takers.
Okay, so you can fill in those circles there. Electron givers are the metals, and electron takers are the nonmetals. Now, just before we move on, and this is only if you're interested. If you're not interested, you can just take a nap for the next minute or so. Okay, just don't talk while we're doing this or go on your phone or whatever. But we're just going to pop in here, and we're going to take a look and find out why does chlorine have a higher electronegativity? Why does it pull electrons better? And why is sodium not as good at pulling electrons? So if we look at this electron here, this one here, it has 11 protons pulling on it. Now, in between that electron and the nucleus, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons pushing outwards. Okay, because negative repels negative, yes? So there are 10 electrons pushing out. So if you have 11 pulls and 10 pushes, what is your net amount of pushing and pulling? You have 11 pulls, 10 pushes. The net is 1 pull, okay? Now let's take a look at chlorine. So we're going to look at this electron. When this electron travels over here now, okay, so that electron's going to come in here. So now that it's at chlorine, how many protons are pulling on that electron? Or sorry, how many protons are pulling on that electron? 17. Okay, so we have 17 protons pulling. And it turns out that the electrons that are in the outer shell don't really pull on it or push on it very much. They do a little bit, they do push on it a little bit, but if they're in the same shell, they don't do much. It's the electrons that are in between that outer electron and the nucleus that do the pushing outward. Does that kind of make sense? Okay, so how many electrons do we actually have pushing outwards? We're only going to look at those inner electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 electrons pushing out. So what is our net pull there? We have a net 7 pull, yeah, because we have 17 things pulling and only 10 things pushing. So which atom has a stronger pull on that electron? Is it the one with the net pull of 7, or is it the one with the net pull of 1? The 7. So if you imagine you have a tug of war, right, and you've got 7 people on one side and 1 person on the other, which side is going to win? I mean, unless you've got 3-year-olds versus like a strong man or something like that. If you've got an equal, like, pullers, it's the 7 will win. So that's basically what's happening here, is that chlorine is better at pulling. Like I said, I'm not going to test you on that particular part of it, but that's why nonmetals are more electronegative, is because they have more protons in relation to their inner electrons. All right, let's go back to Tyler.
Electrons always move from the metal to the nonmetal. And in ionic bonding, because of that, the metals always become positively charged because they lose electrons, and the nonmetals always become negatively charged because they gain electrons. It's all about electronegativity, the greediness of an atom for electrons. Now I want to talk a little bit about the shape and structure that ionic compounds make. Okay, so we've got sodium here, we got chlorine here, and we've talked about how they get opposite charges and they end up sticking together, forming a shape kind of like this. Okay, but so far, we've only talked about two atoms, one of each. In nature, rarely would we find just two atoms, okay? Usually, there are going to be a lot more than two atoms that want to exchange electrons and combine together. So what happens when we have a bunch of atoms that could all do ionic bonding?
What happens when we have a bunch of atoms that can all do ionic bonding? Anyone know what structure we get? We get a crystal lattice, bingo. Yep.
Okay, well, what you might want to think of is each pair of these atoms could form a structure kind of like this.
What do we call that pair of ions, the positive and the negative together? What is that called? That's called a formula unit. Let's write that one in there.
Okay.
Whoops.
But
so where did it go? There it is. Oh, now it's not going to move for me. Okay. This thing right here, that is a formula unit. It is a single unit of an ionic compound. It's made of positive ions and negative ions. Okay.
here's the thing. These guys wouldn't stay separate. Okay, this is super important. They wouldn't stay separate because...
Why wouldn't they stay separate? Tell your partner, why would these three things not stay separate? Well, what's going to happen if this gets anywhere near this one? They'll attract, this negative will attract to that positive, and that positive will attract to that negative, and they'll snap together just like a pair of magnets. Excuse me.
Opposite charges attract, not only in groups of two. Okay, so this positive and this negative, they're attracted to each other, but this positively charged sodium will also be attracted to this negatively charged chloride over here. Okay, so these two things are going to end up connecting to each other because of that attraction, right? And then there's this guy over here, and this positively charged sodium could be attracted to this negatively charged chloride, and this negative charge could be attracted to this positive charge. So this will come together just like here. Okay, and so we start building a much bigger shape. If we get a bunch of these sodium and chlorine atoms getting charges and coming together, we're going to end up with a shape like this. This is called a lattice structure, okay? And you can see how these ions are packed really closely together and how they're making this larger shape.
Okay, so we can make sure we fill in that blank. And we could even call it a crystal lattice structure because we already know that. They fit together in a crystal lattice structure. And you'll notice here in this first one, we have a negative ion, this one here. It is surrounded by 4 positive ions. When we look at this positive ion over here, it is surrounded by 4 negative ions. That's a really stable thing because positive wants to be close to negative whenever possible. And it wants to be as far from positive as it possibly can. Even though we often only focus on a single unit called a formula unit, always keep in mind we are really dealing with a lattice structure. The lattice structure, also known as a crystal lattice. All right, let's let Tyler finish up his thing here.
Okay, here we have a negative ion and it's surrounded by 4 positive ions because they're all attracted together, okay? And over here, we've got a positive ion that's surrounded by a whole bunch of negatively charged ions. And just in general through the lattice structure, we alternate plus, minus, plus, minus, plus, minus, because all of these opposite charges are attracting together to make this lattice structure. So the important thing to keep in mind is that ionic bonding, when you're talking about more than just 2 atoms, it doesn't only make these small groups of 2, but these groups are going to be attracted to each other, and they are going to make much bigger structures that are going to become these lattice structures. So that's super important when you're thinking about the structure of ionic compounds. Now, as we go forward, we'll probably continue focusing on just 2 atoms at a time. But whenever you see a shape like this, keep in mind that it's just one part of a bigger lattice structure that you get when a whole bunch of these different units come together. Okay, finally, let's just talk naming really quickly. Okay, so when this ionic bond forms, we start with sodium, Na, and chlorine, Cl. Okay, sodium loses one of its electrons to chlorine, so that gives us a sodium ion, which we can abbreviate as Na+. And since chlorine gets an extra electron,
what happens to the name? Ide.
It becomes a chloride ion, Cl-.
So you can fill in sodium ion and chloride ion. This is on page 28. Let's go there together. Make sure we're all in the same place. So on page 28, we have the sodium ion and the chlor. Because it's a negative ion, it takes that ide ending. Now, for every 1 sodium, there is 1 chloride. So what would the formula be for this compound? NaCl. Because remember, if there are no subscripts, what's a subscript? It's one of those little tiny numbers down at the bottom. If there's no subscript, that means how many atoms or ions? It means one atom. Okay, so it's one Na to one Cl. Very good. Now, we can just do the rest of this without Tyler. It's okay. A very common mistake that people make when they are writing the formula is to put the charges in there. But we don't do that. Okay, we just don't. So you just write NaCl. Because the entire thing is neutral, because positive one cancels negative one, we just leave it and we don't write the charges. The separate ions, when they're apart, we would write them with the ion charges, but when they are together, no charges. Also, don't write the charges in the name. Sodium, don't write a plus. Chloride, don't write a minus. And that is it. So what I'm going to do is I'm going to give you a few minutes to work on page 29. If you finish that, you can do page 33. Okay, and what I'm going to do actually is I'm going to try and get one of the demos set up for the lab because it'll be a good review for the people who weren't here of Bunsen burner safety, and you'll get to start the lab today. Okay. Cancel. There we are. Hi. The net charge of an ionic compound must be neutral. Uh-huh. You gotta have the same positives as negatives.
This is like a not two. That's oh no, no. Yeah, so eliminate the first. Okay. About that. One opposite. What do you?
Because it is. No. In the same way that if you have water, right? If I got water and I've got a bunch of water molecules, all the molecules are the same, so that's pure. Okay? Each of these are the same as each other. This is the same as this is yeah. Does that make sense? So it is pure. Okay, and if you were to like look at this, it would all be identical. Like it would all have the same properties, and if you had to separate it, I know how much you use like a chemical reaction. Okay? Yeah. Okay. How much of the
You think they can?
Yeah. I don't need flashes. Flash is gone for a walk.
As you know, I was chasing the I was so hungry. You're always. That's about the baby. I was feeling all the hungry, but I don't think that. I don't know. The baby's like my lunch. I completely forgot about it until I was 7. Yeah.
All right, my friends. I'm going to come around with a sample of iron. Does everyone have this sheet? Can you look at it and please point to the word iron? Where it says iron, you'll notice right beside it, it says that's the substance. It says formula of the substance. Do you know the formula for iron? It is Fe. So what you're going to do is you are going to write Fe. And what I'm going to do is I'm going to come around and give you like a little dish and just put some iron in that dish. And you're going to make as many observations about it as possible. Okay, so you're going to look at its color, its size, its shape. Is it shiny? Is it dull? Like, what is it like? Okay, so at each desk, I'm just going to put one of these. There you go. Okay, and you're going to fill in those properties on your sheet. When you're done with it, it's okay. This one's better. Okay. Pardon me? Don't taste it. No.
Don't do that without it. Listen to the properties. Solid,
Yes, you may.
I don't say great production. You can't digest. Some stuff you can polish for you up in clear ways. Yeah, it's nice. Okay, why not? You can't do that all the time for you.
So properties, say what you see. Absolutely. So put both parentheses properties, write what you see. Okay? We have a big container. Oh, you can have a big
container, boy.
Okay, and then this one I have here. This is
Great job.
Well, only write down things you can observe. Okay, so don't be like, it's a good conductor of electricity. Have you tested it? No. So just write down things you can actually see or smell, or even you can even touch these things. Although if you touch the sulfur, you will want to wash your hands afterwards because it will make you a little bit stinky. But you can smell the sulfur if you want to. Yeah. Uh-huh. This next one is the sulfur. Okay. Iron. Symbol there. Yeah. We're away on the safety day. Okay, you guys will be doing your article left. Okay. Yes. Yeah. Some salt. Great. I don't know shiny your adult. Is it shiny adult? Okay, fair enough. Alright, so this is sulfur. No. Okay. So this one is an iron. Really? Anyone who didn't get a sulfur yet? Everyone got a sulfur? Did you guys get a sulfur? No, you did not. Yeah.
I can't smell. Yeah. I'm not saying we can't stop it. It's not. No, I think it's yeah, I was right. Exactly. Oh, yeah. You were worried about why does it? Wait,
So that's another property you can observe about the iron.
What's the other thing?
Yeah, that one more thing.
Oh, yeah. This
Nothing.
I'm so shocked. There's no ring. No, I Fascinating over iron. No. I was. Destroyed the iron. Oh, yeah. Right. How are you?
Iron is notable, yeah, but not this stuff because it's been used for other ones. Alright, let's do
Don't store it. I'll stay there for like.
Alright.
No, don't. No. There wasn't. Yeah, we have that.
Alright, Alex, the iron and the sulfur. Oh, wow. And then, and can you seal this iron? Oh! I'm gonna take 5 grams and react it with 2.5 grams of. Yeah. It's close enough. It's close enough. All right, we did it. We did it.
I was
Who's not seen your magnet? Everyone seen your magnet? Except for you guys.
Why? Put the stuff back in your skin. I think that. Back in your. We're just gonna balance all of there as well. Yeah. All right. This is iron now.
Our magnet now. Let's see what it does. Super exciting, right?
No, it's fine. Iron. I can't breathe. Dude, this dollar bill. Okay, look at it. What? No. Yeah, well.
Okay, friends, you're going to meet me over at the Pinkwood. Meet me over here.
That's what I did.
Okay, so first thing I'm going to do is I'm going to show you how to use a pair of test tube tongs. Okay, you squish it to open them, and then they close. So what do you do to open them? Squish them. Okay, so you squish open. All right, and then you just let it. You don't squish it to hold it. You just let it rest. Okay, this is going to allow us to heat up this test tube without getting my fingers too close to the flame. Okay, now what do you think I'm going to put in my test tube? I'm going to put some sulfur in there and the iron. There. Okay, and now I'm going to give it a little shake. Make sure it's all mixed up. All right, and on your sheet, you're going to go to 2B.
Oh, I think.
Your sheet. That's okay. We can fill it in afterwards too. This is the mixture. What kind of a mixture is this? It is a mechanical mixture. Is it possible, and I have a little bit just in here, would it be possible for me to separate the iron from the sulfur? How can we do that? I could use a magnet, okay, and it would separate it out. Now, what we're going to do is we're going to turn this gas on, and where's my striker?
Yes, here.
Twice. Can you guys check your gas and make sure all the gas is off? Oh, perfect. Thank you. Excuse me. That's the one. Can everyone, actually, can I get a moment? Can you guys go check all of these and make sure they're perpendicular, not parallel? Otherwise, we're going to be swamped out by the gas. All of them.
She ignores us.
And then you can come back. All right, moving back over here. If you were away, this is especially important. So, Ryan, where's Ryan? Come up to the front. All right, ish. All right, who else was away for Bunsen burners? You were away. You were away. You were away. Tiana, you were away. Okay, you were away. So make sure, Tiana, come up closer. So just come in here, okay? So things you need to know about the Bunsen burner are, there is a little nozzle here, and these girls can just sneak through there, perfect, okay? There's a little valve here, and if I remove it, you can see on it, there's a black rubber O-ring. Can you see that? Okay, can you see that little black rubber O-rings? Yeah? Okay, that black rubber O-ring prevents the gas from coming out the side, which means we want it to go in far enough that we can hardly see any of the O-rings, okay? But we don't want it all the way in because otherwise the gas will be blocked off completely, so we won't be able to light it, okay? So what we're gonna do is, oh, and the other thing is the windows here should be closed when you start, otherwise the air will tend to blow it out, okay? Because this will let in the air. And this will be cool enough for you to touch. Everyone else, I want you to tell them all the safety rules. What's one safety rule? Don't touch the fire. What's another rule? You said one? Roll up your sleeves. Do not turn your back on the flame. What else? Tie back your hair. Do not leave a flame unattended. What should you do if you catch on fire? Stop, drop, and roll. I've never had a student catch on fire. Don't be the first one. Okay? So, in it goes. And I'm going to close the windows. There we go. All right. This one probably been on for a while, so we might need to wait for the air to clear out the water. So when we mix these, was that a chemical change or a physical change? That was a physical change, and we can undo it with another physical change when we separate it using a magnet. Now let's find out what happens when we heat it, if I can get this thing lit. Okay, I'll put down to it, I can get this lit. There we go, okay. How do I make the flame hotter? I open the windows. These ones are a little steep. I don't want to open everything. Okay, I'm going to turn out the light so you can see the flame. See the flame? All right, and I'm going to, can I turn on the fan? Not really. So what I'm going to do is I'm going to close this so that any gas that comes out, you won't have to like smell it, okay? And then, if I were doing this outside the fume hood, which direction would I point this? Would I point it this way? Towards you? No, I would try and point it away from me. Hey guys, if you're not paying attention, you're not getting the safety rules. Anytime you're heating something, you need to point it away from yourself and away from everybody else. Okay? And you move it around in the flame so that no one part gets too hot. Now I can actually point it whatever way I want because I've got a sheet of glass in between. Okay? Now it'll just allow me to get a little bit more thing. What has happened? Can you see it? Does it look like it used to? No. Look anything like it used to? No. Okay. Let's turn this off so I can let you guys see it now. Okay, it's still bubbling a little bit. All right, so we've had some melting take place, and we've had some, yeah. Let's either just a little bit more. All right, now it does still smell pretty stinky. So what I'm gonna do is I'm gonna leave it in there. And I am going to show you from last year and the year before. Be careful not to touch this. What I did is I actually took the test tube and I broke it open with a hammer. Okay, and you can see what it looks like now, and it looks significantly different from either sulfur or iron. Okay, so we can pass this around so everyone can take a look at that. Yeah. All right. And we're almost out of time, so if you don't get a chance to write down your observations of that today, you can get it tomorrow. Okay, you guys can go sit down. Unless you want to take a look at this one.
Do you know that Ben Albertine shellfish?
What? I'm not big. I don't.
Hey, go sit. Shh. You have two choices now. Choice A, you're going to hold on to your lab paper and make sure you don't lose it until next day. Option B, you can put your name on it and hand it in here. So if you're a person who's like, this is going to get to the bottom of my bag, I'm going to lose it, make sure your name's on it, hand it in, and I will hold on to it for you. If you won't lose it, feel free to put it in your bag and keep it safe yourself. Okay? Yes. Yes. Sulfur, I'll collect it. Okay? Don't worry about the sulfur and the iron. I'll put it for lunch. Okay? Okay, ladies and gentlemen. 5, 4, 3, 2, 1. You should be looking up here. What is your homework? 29 and 33. I know most of you have done 29. Maybe you've done 33. Maybe you haven't. That's the other homework, okay? Hey, Gavin. All right. Yeah, just pop it in there. Perfect. Thank you. Ooh, garbage? My desk.
What, are we not on the garbage?
No. Oh, you weren't here. Okay, all the garbage cans are now out in the hallway.
Oh,
Thank you so much. And that one can just go down there. So yeah, we don't have garbage in the class anymore. Yes, it's usually implemented, which is why I have my own little garbage can, but I only use it for like dry goods, okay, because I don't want any mice, because there are mice around. So it's like if it's, I think so, yes. I don't know why science doesn't get them there. We have a lot of stuff, yeah. So we do have a couple in the back room, so if you were allowed, I'll bring that, okay? And use the lab. But yeah, normally, and don't worry, you can just leave the classroom to go put it on the garbage can, okay? And you don't even have to ask, you can just be like, pretend it's part of the classroom. It's like having, anyway, yeah. But yeah, I'll just be,
Is plans and corrections again?
no,
Okay.
we're good today. Yes. Yes. Just leave your arrow yourself. You can put your phone and do that. Yeah, okay.
These that smell like grass too.
Right.
When did I see this little? You should ask me. No, you want to say my phone? Thank you. What's last time? I said it. Oh, no. How do you like that? That's sweet. Yeah, no, it's not like that in the days too. Little late stuff. Little late. You just went on with it. I got there.
Yes, yeah. Sorry about that.
Just a reminder, there is a social studies meeting happening in 5 minutes in room 215. Social studies meeting happening in 5 minutes in room 215. Thank you.
I'm anyway now.
Because we were using gas in here earlier, and it has not yet finished working its way out of the system. Actually, let's make sure we get this fan on. That'll help us get out.
Yeah, I need a Oh, you're no, we got blue. No, are you home?